Hey guys, today we're looking at 2.1, which is our cofunction identities, and we're going to do a little review of some special right triangles at the end of it. So the first thing that we're going to do is review our SOHCAHTOA. So for example 1, I want you to find sine, cosine, and tangent values for angles A and angles B and angle B in this triangle right here. So pause the video, go ahead and do that, review that, see if you can do that on your own, and then we'll talk about what the answers are. So for angle A, if I'm looking at sine of angle A would be 7 over 25. Cosine of angle A should be 24 over 25. And tangent of angle A should be 7 over 24. Then when I move to angle B, remember our opposite and our adjacent is going to change, but our hypotenuse is still the same. When I go to angle B, sine of B would be 24 over 25. Cosine of B would be 7 over 25. And tangent of B would be 24 over 7. Now let's talk about these and see if there's any similarities or differences, any patterns, anything you notice here. So you may have noticed that your sine from A is now your cosine for B. Your sine from B is now your cosine from A. So those kind of switched places there. And then your tangents literally just flipped the fraction, which remember we call those reciprocals. So your tangent of A is the reciprocal in tangent B. So these relationships are not just a coincidence. So that brings us to our cofunction identities here. So our cofunction identity that we're going to start with is talking about sine of A is equal to cosine of 90 degrees minus A. If you look at this triangle that we were talking about in example 1, it is a 90-degree over here for angle C, so it is a right triangle. And remember, all of our angles in a triangle add up to 180 degrees. So if angle C is 90 degrees, then that means that angle A and angle B together have to add up to 90 degrees to get to that 180 for the whole triangle. So that means that they are complementary angles and they then fit into this cofunction identity right here. If I'm looking at sine of A, well, 90 minus A would have been our angle B up here in our triangle. And so sine of A would be the cosine of B if we were talking about our triangle up there. And so that 90 minus A matches with our triangle there. Now, in our cofunction identities, I just say 90 degrees minus A because we won't always have a triangle exactly like that where we have two separate angles we're talking about. Sometimes we just have a sine of A and we don't have a whole triangle. We don't even have a second angle to look at. So sine of A is equal to cosine of 90 minus A. And cosine of A would be sine of 90 minus A. So works back and forth. Then remember, both of those have reciprocals that go with them. The reciprocal of sine is cosecant. The reciprocal of cosine is secant. So their reciprocals are going to have the same relationship. Cosecant of A is equal to secant of 90 minus A, and secant of A is equal to cosecant of 90 minus A. Then our other cofunction identities over here are that tangent of A is equal to cotangent of 90 minus A, and cotangent of A is equal to tangent of 90 minus A. Tangent is an interesting one where it is both the reciprocal and the cofunction for cotangent and vice versa. And this is kind of where that co comes from, sine and cosine, secant and cosecant, tangent and cotangent. Cofunction identities with the cos of each other, sine, cosine, secant, cosecant, tangent, cotangent. So let's do some examples here. Example 2 says write each function in terms of its cofunction. This is what I was talking about. We only have one angle here, so that's our A, and we need to write it in terms of its cofunction. If we're starting with cosine of 52, the cofunction for cosine would be sine. So this would be, oh, let's get the pen instead of the highlighter, sine of 90 degrees minus 52 degrees. So the sine of 38 degrees. And what that means is that the sine of 38 degrees is going to have the exact same value as the cosine of 52 degrees. They're going to equal the same thing. Over here, I've got tangent of 71. So the cofunction for that would be cotangent. So the cotangent of 90 degrees minus 71 degrees. So I get the cotangent of 19 degrees. So the cotangent of 19 degrees would equal the same thing as the tangent of 71 degrees. And then secant of 24 degrees, the cofunction for secant is cosecant. So cosecant of 90 degrees minus 24 degrees. So I would get the cosecant of 66 degrees. So the cosecant of 66 degrees is going to equal the same thing as the secant of 24 degrees. Now, remember, we already know our reciprocal identities. Now we're adding in these cofunction identities, which is a different pairing. So you need to make sure that you're keeping those straight. Your cofunctions pair differently than your reciprocal functions. Just make sure that you're aware of that. And they can be used to solve equations when you have different pairs in the equations. So in our last set of notes, we talked about how we could use our reciprocals to help us solve equations. Now we're going to talk about how we can use our cofunctions. So if you look right here at example 3, it says find one solution for the equation. Assume all angles involved are acute angles. So if I'm looking at acute angles, that means they would be less than 90. So we could use our cofunction identity here, because if they're less than 90, we can do 90 minus whatever it is. Now, if I'm looking at cosine and sine, those are cofunctions. So I would use my cofunctions, the cofunction identities here to help me solve this instead of what we did in our last set of notes where we used our reciprocal identities because we had the reciprocal pairs in our equation. So what's going to happen is when you get your test, you're going to have an equation that just says solve this equation, but it's not going to tell you solve it using the cofunction identities or solve it using the reciprocal identities. You're going to have to be able to look at it and see, okay, I've got cosine and sine. What is the relationship between those two? You're going to have to be familiar with that and know that and be able to figure that out. So cosine and sine are cofunctions. It doesn't matter if I change the sine to a cosine or if I change the cosine to a sine. So let's go ahead and change, let's do the right side, the sine to a cosine. So what that means is this left side stays as cosine of y plus 4 degrees. And this right side is now going to be the cosine of 90 minus that 3y plus 2 degrees. Once we get to a cosine equals a cosine, we can do what we did the last set of notes where we can just look at what was inside of our trig functions. Because if I have a cosine equals a cosine, then whatever's inside the cosines have to equal each other. That means y plus 4 has to equal 90 minus my 3y plus 2. I am subtracting that whole 3y plus 2, so I'm going to go ahead and distribute that negative. So y plus 4 is equal to 90 minus 3y minus 2. And I can combine my like terms here. I get y plus 4 is equal to 88 minus 3y. I'm going to add my 3y over, and I'm going to subtract 4. You can do them in separate steps or in the same step like I am here. So I get 4y is equal to 88 minus 4 is 84. And then I divide both sides by 4 to get that y is equal to 21 degrees. So my solution here would be that y is equal to 21, and then I could plug it back into the equation if I needed to. Okay, the next one I have tangent and cotangent. So with this one, tangent and cotangent are reciprocal identities, but they're also cofunction identities. So when we're talking about the reciprocal identities, that's when I have 1 over something. And so since this equation doesn't have any fractions, it doesn't have 1 over tangent or 1 over cotangent, this is where using the cofunction identity is going to be more helpful because I don't have any of the fractions that could help me out like we did in the last set of notes. So let's go ahead and change our cotangent to a tangent using our cofunction identity. So the left side, once again, is just going to stay how it was. And my right side is going to change to a tangent of 90 minus the x plus 18 degrees. I'm going to just look at what was inside of my tangents now. So 2x minus 18 is going to equal the 90 minus the x plus 18. I'm going to distribute. So I get 2x minus 18 is equal to 90 minus x minus 18. What I kind of notice here is that if I look at this, I can see that if I were to add 18 to both sides, that's going to cancel that out. So I get 2x is equal to 90 minus x. I can add x over, and I get 3x is equal to 90. And then I can divide by 3, and I get that x is equal to 30 degrees. So that's how you can use your cofunctions to help you solve equations. The other thing that you can use your cofunctions to help you with is remembering how your functions either increase or decrease based off of the angle increasing. So I've got this table right here, and you can see like as our angle increases, so we start with a small one here, we get a little bit bigger in our middle picture and bigger in our last picture. The y is also increasing, so our opposite side is increasing, but you'll notice our x, our adjacent side, is decreasing. So as your adjacent and opposite sides change lengths, they do change at the same proportion. So that does mean that your r, your hypotenuse, is a fixed value. That stays the same. But as y increases and x decreases, that is going to change your trig values. So as a increases, your angle increases, y increases, and x decreases. So that means that sine, secant, and tangent are going to increase, but cosine, cosecant, and cotangent are going to decrease. So you can group them by the co-functions here to help you remember what's increasing versus decreasing. And the reason this is helpful is for problems that look like 4 here. So it says determine whether each statement is true or false. So if I have the sine of 21 degrees is greater than the sine of 18 degrees, I need to see if that's a true statement or a false statement. I'm going to start by looking at the angle measures. I can see that 21 degrees is a bigger angle than 18 degrees. So based off of my table, if I'm looking at sine, as the angle gets bigger, sine gets bigger as well. Sine is increasing. So if this is my bigger angle, then the sine would also be bigger. So this is a true statement. Sine of 21 degrees would be bigger than sine of 18 degrees. If I look at the next one, it says the secant of 56 degrees is less than or equal to the secant of 49 degrees. So if I'm looking at this, 56 degrees is greater than 49 degrees. And here it says that secant should increase as my angle gets bigger. So secant of 56 should be bigger than secant of 49. So this sign is facing the wrong way. This would be a false statement. So it can help you kind of figure out whether statements like this are true or false. So that's our cofunction identities, adding to our list of identities that we're learning as we go through trigonometry and adding to that tool belt that you have. Remember, you do have to memorize these, be really familiar with these as we go through the semester. What we're going to do now is do a little bit of a review of special right triangles because these are going to be really helpful for us as we go through the semester as well. So Remember for your 30, 60, 90 special right triangle, I'm going to make our little chart here that we make in geometry. I have my 30-degree angle, my 60-degree angle, and my 90-degree angle. When I am looking at the picture that's here in my table, it's just got 1, square root of 3, and 2. That is the most basic of what the sides could be, and they follow those same ratios. So as the sides get bigger, they will still stick with that same ratio. So across from the 30-degree angle here is 1, but let's say that that was L. Then that means as that gets bigger, so does the value across from the 60-degree angle. Instead of just being square root of 3, that would be L square root of 3. And across from the 90-degree angle would be 2L. You could use X or Y or whatever letter. I use L for length of the side length. Okay, you can make a similar table for your 45, 45, 90 triangle. So 45 degrees, 45 degrees, 90 degrees. If I'm looking at this triangle, you can see across from the 45-degree angles are both 1. So both of those would just be L. And then across from the 90-degree angle is the square root of 2. So that one would go up as L square root of 2 as our sides change. So there's our two ratios for how we work through our special right triangles. Now, this can also be helpful as we're looking through our trig, because remember, this is trigonometry. And no matter what our side lengths are, our trig functions are always going to simplify down to the same values because those side lengths, those ratios will always simplify down to the same trig values. So I've got a table here. I've already given you all of the trig values for 30 degrees and 45 degrees, but let's find the ones for 60 degrees. So if I look at my special right triangle that has 60 degrees in it, I've got my hypotenuse over here across from the 90-degree angle, my adjacent down here next to my 60, and my opposite over here, opposite the 60-degree angle. So using my SOHCAHTOA, the sine of 60 degrees would be opposite over hypotenuse. So that would be the square root of 3 over 2. My cosine would be adjacent over hypotenuse. So that would be 1 over 2, 1/2. My tangent would be opposite over adjacent. So that would be the square root of 3 over 1, which just simplifies down to the square root of 3. And then remember from here, I can use my reciprocal identities to find the other 3. So remember the reciprocal for cosecant is sine. So if I know sine, I can find cosecant. I can just flip my sign. So 2 over the square root of 3. I can't leave it like that though. I do need to rationalize it. So I'm going to multiply top and bottom by the square root of 3. And I get 2 square root of 3 over 3. If I'm looking at secant for reciprocal identities, that's paired with cosine. So I would just flip my cosine and get 2 over 1, which just simplifies to 2. And cotangent and tangent are paired together. So I would flip my tangent, which would give me 1 over the square root of 3. I would need to rationalize my denominator. So I would get the square root of 3 over 3 when I rationalize my denominator. These are very, very common angles. That's why their right triangles are special right triangles because 30, 60, 45, very, very common angles. So all of these values in this table here are going to be values that are going to come up a lot in this class and when you go on to calculus after this class. They come up in something that we call the unit circle that we will talk about in a later unit, actually in chapter 3, so the one right after this. So these are going to be values that you're going to need to memorize, that you're going to need to know. So I would definitely suggest memorizing this table. Ooh, I cannot write today. Okay, now if you don't want to memorize these, if you don't want to memorize this whole table, you could draw your special right triangles and use your SOHCAHTOA to find the values over and over again if you really, really wanted to. But I promise you, the amount of times we're going to use this in our class, and specifically the 30 degrees, 40 degrees, and 45 degrees and 60 degrees, you're going to just start knowing these like how you know that the square root of 25 is 5. They're going to just become second nature to you. So I know it seems a little daunting right now, all of the things that you have to memorize, but you're just going to start becoming so familiar with them. You're just going to have them memorized before you even know it. The last thing we're going to look at is solving a problem that has special right triangles in it, remembering how to do this from geometry. So it says find the exact value of each part labeled with a variable in the figure, which means we need to find P, Q, and R. I would start over here with this triangle that has a side labeled. It tells me over here that this side is 15, and that's across from a 45-degree angle, which means down here across from this 45-degree angle should be the exact same side length. So P would be 15. Then looking up at my nice handy dandy little chart that I have right here for my 30, 60, 90 and 45, 45, 90, I can see that if my 45 and 45-degree angles have L and L, then across from the 90 should be L square root of 2. So down here, across from this 90 right here, R should equal 15 square root of 2 because this 15 was our L for that triangle. Now, the next triangle is the one where it's going to be a little bit more work. We know that this angle up here in the top is 30 degrees. This little box means that this angle down here is 90 degrees, which then tells us that this one has to be 60 degrees. So I know that that's a 30, 60, 90. I'm going to go ahead because it helps me visualize a little bit better, make my little chart with my 30-degree angle, 60-degree angle, and 90-degree angle. So remember, across from 30 is L, across from my 60 is L squared root of 3, and across from my 90 is 2L. So L squared root of 3, 2L. So if I'm looking, across from my 30 right here is the Q that I'm trying to find. Across from my 60 right here is the R that I already know is 15 square root of 2. So I'm going to use that this 15 square root of 2 has to equal the L square root of 3 and set up an equation. 15 square root of 2 has to equal L square root of 3. So to solve for L, I can just divide both sides by the square root of 3. L is going to equal 15 square root of 2 over square root of 3. Now I do have to rationalize my denominator, so I'm going to multiply top and bottom by the square root of 3. So I get 15 square root of 6 over 3. And then I do have to simplify that fraction. So I do end up getting 5 square root of 6. So if L equals 5 square root of 6, then I know that that's what Q equals. And I've found all of the labeled parts in this picture that I need to find. Okay, that's it for this set of notes. Make sure that you guys get started on your assignment. Let me know if you have any questions, and y'all have a good day.